is go over a problem similar to what we did on Monday, or whenever you watch the video. So if you want to take a second to write this function down, f of x equals 3x cubed plus 5x squared minus 12x minus 20, all divided by x squared plus 2x minus 6. And we're supposed to find the domain, the intercepts, any vertical asymptotes, and any holes, if there are any, right? So you're not guaranteed any of these things. You are guaranteed a domain, though. Okay, the first thing I need to do is factor. The numerator is a cubic, so we're going to factor that by grouping, and I'm just going to rewrite it. So you just got to remember that subtracting is the same thing as adding a negative, so I'm going to add a little plus sign in here and group the negative with that second group, right? So we're going to factor out the only thing these two have in common, which is an x squared, and we're left with 3x plus 5. And then negative 12 and negative 20, we want a 3x plus 5, right? So we think, what is the common factor? We're going to go ahead and factor out a negative 4 so that when I do factor it, I get 3x plus 5. Okay? Then the common factor between these two terms, right? It's like saying x squared y minus 4y. The common factor is y, so you could factor out the y. And you've got that. Well, our y is the binomial 3x plus 5. So we're going to factor out a 3x plus 5. And we're left with x squared minus 4. But x squared minus 4 is a difference of perfect squares, so this in fact equals 3x plus 5 times x plus 2 times x minus 2. And then if we factor the denominator, we're looking for factors of negative 6 that add up to positive 2. So factors of 6, oh, no, I'm pretty sure I meant that to be an 8. Yeah, I'm going to change that. Pretty sure. Yeah. Okay. So then when you factor that, factors of negative 8 that add up to positive 2 are positive 4 and negative 2. All right. So here is our factored form of this rational function, and let's look at the factors, right? We've got 3 factors in the numerator, we've got 2 factors in the denominator. So right off the bat, I know that the denominator equals 0 at negative 4 and at 2. So these are the two values that x cannot equal because they won't exist, right? So my domain is going to have to be everything but those numbers. So negative infinity to negative 4, negative 4 to 2, and 2 to infinity. Or we could say all real numbers, x not equal to these two. Okay, then I'm going to go ahead and skip to thinking about common factors so that I can go ahead and get that out of the way. I notice that I have x minus 2 in the numerator and denominator, which means that is a hole in the graph, okay? So that we've got a hole at x equals 2, but remember that that's a location. So what we're going to do is we're going to write down what's left over of the function. 3x plus 5 times x plus 2 divided by x plus 4. So this is what the function basically looks like. It's got a hole in the graph at 2 because of that common factor right there. So we're going to plug 2 into what's left over. So I've got 6 plus 5, 11 times 4 divided by 6. Yeah? So that's 2 and that's 3, so 22 thirds. Okay, and then let's talk about what's left over. The other thing in the denominator is this x plus 4. So remember, if it's a factor in the denominator and only the denominator, or more in the denominator than the numerator, then it is a vertical asymptote. So we do have a vertical asymptote at x equals negative 4. Okay? So that takes care of that. We've taken care of these two. So then the question is, what are these right here? So just remind ourselves that the numerator, those factors in the numerator, the zeros of those, x equals negative 5 thirds and x equals negative 2, those are the x-intercepts of the graph, because that's when the whole function equals 0, right? So at negative 5 thirds is 0 times a bunch of other crap divided by a bunch of crap, not 0. So 0 divided by a number is 0, and then same thing with negative 2. So both of those are x-intercepts. So we've got negative 5 thirds, comma 0, and negative 2, comma 0. And then y-intercept, remember that a y-intercept is when x equals 0. So far, none of these have claimed x equals 0 as like a vertical asymptote or a hole. So I'm going to go ahead and go 0, comma, and I like to go back to the original. And if I look at everything, and I just think all the x's go away because I'm plugging in x equals 0, I'm left with negative 20 divided by negative 8. So that's a positive 10 force 5 halves. Yeah? Okay, so positive 5/2. And let's look at that real quick. So I'm going to go ahead and just type in my rational function 3x raised to the third plus 5x squared minus 12x minus 20 all divided by x squared plus 2x minus 8. Okay, so I know that a lot of things are happening at like -4 and 2. We've got the hole in the graph, we got vertical asymptotes, so I don't need to go very far out. I'm going to go -6 to 6. And as far as y values, I really don't know. I'm going to go -20 to 20 and just see what happens, and then I'll just play around. Where's my, oh, my vertical asymptote is at -4. Okay, so I'm going to have to zoom out a little bit more. So we're going to go -10 to 10. Actually, I'm going to lean more on this side. And I'm going to go -50 to 50. Okay, there we go. Yeah, as with these rational functions, the y values can get really large. Okay, so this is kind of interesting. It has this thing called a slant asymptote, which we're going to talk more about today. It's called an oblique or a slant asymptote, as opposed to a horizontal asymptote. And this is something that occurs when you have rational functions and the higher power is in the numerator. But we'll talk more about that in a second. So, okay, you can see I've got my vertical asymptote at x equals -4, so 1, 2, 3, 4, -4 right there. We can see that we've got x-intercepts at -5/3 and -2, so those are really close to each other. So let's go ahead and zoom in on that. I'm going to go -5/3 is like, okay, so that we'll go -3 to -1. And we're going to go -10 to 10. Let's see if we can see it. I want to go, okay, -2 to 2. Okay, so we zoomed in and we can see that we cross at -2 and then we cross again at -5/3. Okay, so those are my two x-intercepts. Let's see if we can see the hole in the graph. So the hole in the graph is at 2/22, right? So that's 7 1/3. So what I'm going to do is I'm going to zoom in around that. I'm going to go 1.5 and 2.5, so I'm going to really get close to x equals 2, right? And then 22/3, like I said, is 7 1/3, so we're going to go 7 and 8 on the y-axis. And so we should be able to see the graph, and there you go. There's a hole. So that is at 7 and 22/3. Okay, so that would be impossible for me to see if I go back to my original window, which was what, -15 10, -50 50, because there's not enough pixels. The pixels are too large, so I wouldn't be able to see over here at 7 10 9 8 7. Yeah, so you can't see the hole in the graph right here because there's not enough pixels. But if you zoom in, then the graph will jump over it. Okay? Alright, so that is to kind of just get us back into what we did the other day. And then we're going to talk about in behavior models and horizontal asymptotes. Well, and just, yeah, in behavior models, because they're not necessarily always going to be horizontal asymptote. So when I teach this, I really like to have everyone graph one of these functions and go to the table and look at what they're approaching. So I'm going to do that with a few of these, and then I'm just going to write down what they're going to, and then we're going to see what we can see. Okay. So I'm going to go ahead and start with this one. So if I go x plus 1 and 2x minus 5, and I go to my table, so second table set, I'm on ask already because it said go to table set, switch to independent to ask instead of auto, go to table and type in the x, okay. So go to my table, and I'm going to type in 1, 100, 10,000, 100,000, well, I'm just going to make it a million, and a lot of zeros. Okay. Alright. So what I can see is that as x gets larger, so x is getting larger and larger and larger, right? So we're going to the right as x goes to positive infinity. This was negative 2/3, and then it was 101 divided by 195, and then it was 0.50018, and then it was 0.5000018, and then it was basically saying it's 1/2. Okay, it doesn't actually reach it, but it's saying, for all intents and purposes, it's 1/2. And I agree. If you go to infinity, this is going to go to a ratio of 1/2, going to positive infinity. As x goes to positive infinity, y goes to 1/2. Now, what about negative? So if I would go here, negative 1, negative 100. Oh, yeah, I can't. Okay. I'm just going to keep typing over. So it went, well, first it was saying 0, negative 1. That's because it's a x-intercept, so that makes sense. And then 99 over 205, well, that's pretty close to a half, right? So if I were to type in negative 10,000, that's getting close to 1/2, 0.49983. And then if I typed in negative 1 with a lot of zeros, it's saying, hey, you're basically a half. So no matter what, in either direction, as x goes to positive infinity and negative infinity, y went to 1/2. Okay. So now let's go to this one. I hate how I wrote that. Oh, it looks terrible. Okay. So if I were to type in just 5 in the numerator, and then 3x plus 10, and I go to the graph. Oh, just kidding. I'm going to the table. So at 1, it's at 5/13, and then it's at 1/62, so it got smaller quite a bit. And then it's at 1 over 6002, it got even smaller. And you see this e to the negative 6, that means move the decimal 6 places this way. We're getting closer and closer to e to the negative 11th. We're getting closer and closer to 0. This is getting smaller and smaller and smaller. And given kind of what we said the other day, that makes sense that it's getting smaller because this is getting larger and that's staying 5, right? 5 divided by an increasingly large number is getting smaller. So as x goes to positive infinity, y is going to 0. Okay. And then negative is going to be doing the same. So as at negative 1 it's at 5/7, but then at negative whatever that was, it's really, really large negative number, you get to basically 0. 0.0000009 zeros and then 1. Okay. All right. So let's talk about this one. So y equals 8x squared divided by 4 minus 10x. I don't want to do that. I want to go to the table. Okay, so let's look at this one. As I get larger, so forget the negative for a second, it was at negative 4/3, and then it was at negative 20,240. Now that's bigger, right? There's a much larger number. This is basically saying, hey, it's negative 8,000, and then this is negative 800,000, and then negative whatever that is, right? It's just got larger and larger and larger. But let's talk about negative. So negative 1, it was at 4/7, and then here it went, it just got really, really large, right? It's positive, though. So in the positive, it went negative, and in the negative, it went positive. Interesting. So when x goes to positive infinity, y went to negative infinity. And when x went to negative infinity, y went to positive infinity. Okay. So I'm going to do 3 more and with a calculator, and then we're going to just talk about it. Okay. I'm going to pick this one. So I've got 14x raised to, just kidding, x raised to the 3rd divided by 8x plus 7x raised to the 3rd. Okay, so I'm going to go to my table, and as x gets larger, the y value 14/15, that's close to 1. That's more than 1, but not quite. Is it over 2? Let's see, 1600, whatever. And then, or 16,000. And then this, okay, 1.999, repeating, and then, well, not repeating, and then 2, and then 2. It's basically saying, hey, we're getting closer and closer to 2. And then if I go negative, let's see, negative 1 was 14/15, similar to that, and then this one, it's saying 2. What if I just do like a negative 1,000? It's saying basically 2, 1.999. Okay. So, interesting. They're both getting closer to 2. So, as x goes to both positive and negative infinity, y went to 2. I need to put my plus and minus there as well. Okay. Let's go to this one. If I go 6x squared plus 1, and then I go 2x raised to the third minus 100x. Okay. Alright, so I'm going to go to my table, and I see that as I get larger, the y value, negative 1/14, 0.030, e to the negative fourth means 4 decimals, so 0.0003, 6, so 0.000003, right? So it looks like it's getting smaller and smaller and smaller and smaller, and in fact, if I go in the other direction, in the negative direction, so it's x getting, x is expanding, right? We're going larger and larger positive x values and larger and larger negative x values. So negative 1,000 is negative 0.003, and then negative 100,000 negative 0.00003, and negative, just kidding, whatever that is. So it's just getting smaller and smaller and smaller, getting closer and closer to 0. So as x is going to positive and negative infinity, y is getting closer and closer to 0. Notice how I'm doing, like, these both went to a number, not 0, so I put them both in red. These are both going to 0. So I'm going to try and find another one where it goes to the infinity. So let's look right here. Negative x to the fourth. X to the fourth. Oh, just kidding. X to the x is not what I want to do. Okay. And then, oh my gosh. Wow. Okay. 2x squared minus 5. Let's go to the table. Okay. So when I'm looking at this, as I go to the positive, 1/3, and then negative 5,001, negative, let's see, is that negative 50 million? So I got really large really quickly. In the negative, this got even larger, and this is even larger. That's a negative, very, very large number. So we're going to say as x goes to positive infinity, y is going to negative infinity. Let's talk about when x goes to negative infinity. So when x goes to negative infinity, so negative 1 was that, negative a lot was very large, very, very large negative number. So that's also negative infinity. Okay, so let's talk about what commonalities they have, or the reason why we had different types doing different things. You might notice, I don't know if you, I'm looking for something real quick. Where did I put it? Oh. You might notice that these two, where it went to a number, right? Well, I don't know if you notice it, but the highest power in the numerator and denominator is the same. The highest power in the numerator and denominator is the same. Which means that when I go to infinity, when I plug in a billion, when I think about what's a billion plus 1, basically a billion. What's 2 billion minus 5? Basically 2 billion. So what's a billion divided by 2 billion? A half, right? If I plug in a billion here, yes, 8 billion is a large number, but a billion cubed is so much larger that this becomes insignificant the larger and larger you get. You're talking about billion, trillion. That becomes much less significant than these terms right here because they have the higher power. And what's 14 divided by 7? 2, right? So in all of the cases where the powers are the same, in the top and the bottom, you're going to level off to that number. So if I were to actually graph this function right here, x plus 1 and 2x minus 5. Let's go regular window. You can see, well, I'm going to zoom into like, okay. Let's go -1 to 3. So I'm also going to graph y equals 1/2 because I'm claiming that that's going to be the end behavior model. And by end behavior model, I mean this is a function that is going to model the end behavior of the function. I'm not talking about the behavior in the center. I'm talking about as it goes out, what's going to model the behavior. So here's my left side and here's my right side of my my horizontal asymptote. And do you see this right here? It goes right through the center of the graph. It's going, so the horizontal asymptote is at 1/2 because that's the ratio at which these two most powerful terms interact with each other. This one right here, it should level off to 2. So I'm going to clear that out and just do it again. 14x raised to the third divided by 8x plus 7x raised to the third. Nope, just kidding. Raised to the third. And I'm going to type in 2. And here I'm going to go, let's go 0 to 3. And I'm going to go -20 to 20. I don't know what it's going to look like, but it should level off at 2. So here is 2. Ooh, this does something interesting. And then there's our horizontal asymptote. So it modeled the end behavior of the function. It had nothing to do with what's happening on the interior, but it does say, hey, the two sides, they're going to level off, right? If I actually did this on a normal window, it's got an interesting graph. And there you go. Okay. So, yeah, in behavior models, as far as this goes, anytime the powers are the same on the top and the bottom, so if we try and look for this, the higher power is 3, so that's on the top. The highest power is 5, well, that's the same, right? So here, we know we're going to have a horizontal asymptote at y equals -9/3, so -3. Because they're going to grow at the same rate. Even though x to the fourth is very powerful, it's not as powerful as x to the fifth. So this will determine the end behavior of the function. And they're the same rate, so -9 divided by 3 is -3. And then let's look. So this one, the higher power is down there. We'll talk about that in a second. This one, they have the same power. So we've got these two terms. 5x divided by -25x, that's 5 divided by -25, so that's -1/5. So this one will have a horizontal asymptote at -1/5. Y equals 1/2 was that horizontal asymptote. Y equals 2 was that horizontal asymptote. Alright, this one right here, the same power is 1 on top and bottom, so that's 6 divided by -2, that's going to be -3. So we've got a horizontal asymptote at y equals -3. The higher power is up here, the higher power is down here, the powers are the same. So these become negligible, and this becomes just 8x squared divided by 2x squared. That might as well just be 4. So the horizontal asymptote is at y equals 4. Okay, so as far as horizontal asymptotes go, if the power in the numerator and denominator, so if f of x divided by g of x, if powers of f of x and g of x are the same, there's a horizontal asymptote at y equals the ratio of leading coefficients. Okay, so for an example, if I had 7x to the third minus 10x to the 7th divided by 40x to the 7th plus 9, whatever this is, right? 900,000. Doesn't really matter. The most powerful term is the x to the 7th, so it would be a horizontal asymptote at y equals -1/4. 10 divided by 4. Okay. So now let's look at for more that had zeros, right? This one went to 0 as we went to both positive and negative infinity. This one went to 0, so we went to both positive and negative infinity. So let's talk about that. Actually, I'm going to go ahead and highlight so I can get those out of the... So don't look at them. Okay. I get a different color for this one. Alright, so we're looking at the ones that are going to 0. So if we look at this one and this one. When we look at what is similar to them, not that you can see it because I've covered it up. The highest power on the numerator here is 2, and the highest power on the denominator here is 3. The highest power in the numerator here is 0, 5x is 0, so it's a constant, divided by 3x plus n, the highest power is 1 there, right? So the thing that they have in common is that the higher power is in the denominator. So when you think about, like, what's the most powerful term right here? So if I were to divide 6x squared by 2x cubed, you know, like, just because we know that when we go to infinity, these become less important. They just, well, it's not like they're not important, but they don't affect the end behavior because they become negligible the larger and larger the x values get. So we're basically dealing with this ratio right here. Well, if I were to divide this, 6 divided by 2 is 3, and x squared divided by x leaves me an x in the denominator. So I might as well be dealing with, in the end, this function right here, 3 over x. Okay? Well, 3 over x, 3 divided by an increasingly large number is just increasingly small, if that makes sense. It's getting closer and closer and closer and closer to 0 because the higher power is in the denominator. So this is going to 0, this is going to 0, higher power is on top, so nope. Higher power is in the denominator, so this one. In fact, if it's going to a number, if it's leveling off to 0, then that means we have a horizontal asymptote at y equals 0. We have a horizontal asymptote at y equals 0. We have a horizontal asymptote at y equals 0. This one right here, the higher power's on top. Here, this one right here, the higher power's in the denominator. This one is going to 0. Power up here is 1, the power on the bottom is 2. So we have a horizontal asymptote at y equals 0. Okay, so what's the rule here? If the power of the numerator, f of x, is less than the power of g of x, if the power of the numerator is less than the power of the denominator, we have a horizontal asymptote at automatically y equals 0. Okay? And so, you know, saying f and g is okay, but sometimes it really helps to just remember to be thinking numerator versus denominator. Okay, so if the power of the numerator is less than the power of the denominator, that means the numerator is growing slower than the denominator, which means the number itself is getting smaller. So that's why they have a horizontal asymptote at y equals 0. Okay, so we've identified what if the powers are the same. We've identified what if the power of the numerator is less than the power of the denominator. So then we have this other option, right? What if the power in the numerator is greater? And that is when we deal with this other situation. So I'm going to kind of generalize, and then I'm going to teach you, like, the trick to, like, actual end behavior models. If you think about the most powerful term right here in the top, it's 8x squared, because it's the only one. And if you think about the most powerful term in the denominator, it's negative 10x. Well, if I simplify that, I get negative 4/5 x, right? So I want you to think about the function negative 4/5 x right quick. It's a linear function with a negative slope. And as I go to negative infinity, the function goes up to positive infinity. As I go to negative infinity, the function goes to positive infinity. And as I go to positive infinity, the function goes to negative infinity. Okay? Meaning, this might as well be modeled by negative 4/5 x. Now, there's a little bit more to it than just negative 4/5 x, but I'll talk about that, like I said, in a minute. Okay, so let's look at this one. Because these are both negative infinity, right? So how can I see that? Well, I'm going to look at this. If I were to simplify negative x to the fourth divided by 2x squared, two of the x's can simplify out, and I'm left with negative x squared divided by 2, or negative 1/2 x squared. Well, let's think about that function. That's a quadratic with a negative leading coefficient. When x goes above positive and negative infinity, the function is going to negative infinity. This becomes an end behavior model, right? So if we look at this one right here, right? The most powerful terms are these two right here. If I were to simplify them, 7 halves x. So in general, the end behavior is going to look like what 7 halves x does, which means 7 halves x is a increasing linear function. So I already know that as x goes to positive infinity, y would go to positive infinity. As x goes to negative infinity, y would go to negative infinity. Okay? And then same right here. Most powerful term, most powerful term. That leaves me with 3 halves x squared. Okay? Well, that's a quadratic, a positive quadratic. Both go to positive infinity. So, if the higher power, the power of f of x, numerator, is greater than power of g of x, the denominator, then you can have a polynomial asymptote. And so this is kind of interesting because when we think about asymptotes, we think about, a dotted vertical or horizontal line. Well, this end behavior model is going to be a quadratic. So in essence, you're going to have, and it's not going to be exactly 3 halves x squared. There's going to be some kind of shift, but I'm going to pretend. So you could have a function that has this, so it does this, and then it does this, and then it does that. So in the end, it's going to look like the quadratic. It's its end behavior model. It models what the ends are going to look like. It doesn't tell you what's going to happen in the interior, but it does model the end behavior. Okay? So, these end behavior model rules, these horizontal asymptote versus, so horizontal asymptotes applies to this and to this. In general, this is end behavior models, if you want to think about that, because this is not a horizontal asymptote, right? So when do we have just a slant asymptote? It's when we have the higher power is only a higher power by a degree of 1, because then that means it's a linear end behavior model, right? So those have a specific name. I'll just go ahead and write that down. Slant slash I'm thinking slash, so I write it. Slash oblique asymptotes. That occurs when the power in the numerator is greater than the power in the denominator by 1 degree, because that means the end behavior model is a linear function. But that's not necessarily just the end behavior model, 3 over x. So we're going to have, well, 3 over x is. This one, 7 halves x. So I'll talk about that in the next video, because I'm going to have to go and stop this.